Hello everyone, welcome back to Diksha Karnataka YouTube channel, and in the Sankalp KCET 2026 it's time for us to move on to the second chapter of your class 12th or second PU, and today I am going to discuss electrostatic potential and capacitance chapter. This is the first part of the chapter, and in this chapter we are basically discussing about electric potential, all the types of electric potential. We'll see in a while what are all we are going to discuss in this lecture and what are all are covered throughout the lectures, how many parts will be there and what are all concepts we will cover in the individual parts. But first, if you have not joined our WhatsApp channel, please join the WhatsApp channel. The link of the lecture PDF, everything will be available through our WhatsApp channel. Whenever we are doing a new video, a new lecture or update video, whatever it is, that will be posted through our WhatsApp channel. So please join that. It is absolutely free and your identity will remain safe, right? Let's see some of our achievement from last year KCET 2025. And as you can see, there are a lot of toppers throughout up to rank 5534, and if you go a little bit beyond this range, we have a lot of students in this range through our exclusive YouTube channel content only. And if you are studying seriously from our lectures, then maybe next year your picture will be here, who knows, right? So let us now go into the chapter details of what are all the concepts involved in this chapter and what are all we are going to cover in different parts of the lecture. So first, electric potential is the topic for today. In this we will discuss potential energy and potential, the difference between energy and potential basically, and their individual meaning. We will also study electric potential due to point charge, electric potential due to system of charges. These all we will study in this lecture. Also we will study about equipotential surface. We will study about the relationship between electric field and voltage. We will also know about potential due to system of charge, potential due to a dipole. So these are all we will be covering in our today's lecture. So everything that I have shown here we will be covering in part 1. In the part 2 of the lecture we will cover conductors and dielectrics. Here we will cover what is a conductor, detailed explanations. There are some important points to remember about conductors and about dielectrics as well. In the dielectrics we have two types of dielectrics, that also we will cover. Then we will cover polarization, what is a polarization, how it is achieved, and what are the difference between polar and non-polar dielectrics. Now last part 3 of the lecture we will be covering capacitor. We will also cover parallel plate capacitor, combination of capacitors, as well as energy stored in the capacitor. So everything involving parallel plate capacitor, capacitance of parallel plate capacitor, everything we will cover in this lecture. So there will be 3 parts on this main 3 parts of the theoretical lectures, as well as we will cover PYQs of KCET in one part and PYQs of JEE in another part. So there will be total 5 parts of this chapter as well. The number of parts will change based on the content of a chapter, and after this chapter, next chapter have some less theoretical content. So in that chapters we will be doing not 3-part chapter. That will not be a 3-part chapter. That will be less number of parts. Now let's see the first concept, electric potential energy. Let us first understand a scenario. What is the scenario? Here we have a charge, okay, capital Q charge, which is kept at some point. We are saying this is kept at origin. Origin means center of everything, right? That is easier for us to understand. So we will say that a charge Q, capital Q, kept at origin at some distance A, at some distance at a point A. Okay, distance we are not thinking right now, but at some distance at point A we have a test charge small q. Now if you remember, I have already explained the meaning of a test charge. Test charge is something which does not affect the original electric field, or it does not have its own electric field, and it only interact with the present electric field. It does not exert its own electric field. So electric field due to small q, we can ignore it. Only electric field due to capital Q is important here. Now if you have a charge, test charge at point A, and you want to move this test charge from point A to point B, right? Now if there is nothing, if this charge is missing, you don't need to do any work to move it. It is very easy to move it because no force is acting on it. So basically you will not need to do any work or spend any energy basically to move this charge, right? Now because this capital Q charge is present over here, you have to do some work. You have to do some work to move this charge from point A to point B. Right? You have to move this charge from point A to point B. Now what work you have to do? That work will be because electric field is a conservative field, that means whatever work you do against the field or by the field, whatever work is being done, that work is stored as energy. That was the definition of potential energy, if you remember, in first PU, but in that case we mostly discussed about gravitational potential energy, right, MGH. Now this is the second potential energy that we are going to discuss, which is electric potential energy. Okay, so whenever you do some work against some existing field, okay, you have to do some work. Now if the existing field is a conservative field, then whatever work that you do, that work is basically stored in the system. So this capital Q will either gain or lose some energy based on their signs. Okay, in this case, for example, I have taken both of them apparently positive, so it will basically lose energy. Okay, if Q is positive, small q is negative, then this small q will gain energy. How it will be calculated, we will see that in a while. Anyway, so once you move this object from point A to point B, the whatever energy is stored in this Q while it is going from A to B, that is called electric potential energy. So work done to move a test charge small q. Now let us go into the mathematical aspect of it. What is the mathematical calculation? So mathematically the work done is given by WAB. Okay, WAB is the work done, right? WAB is the work done to move the charge. Okay, and here F external into dr. Why it is written like that? Because if you see that the force, this external force, what is this external force, by the way? External force is given by Q into E. Whatever is the electric field at the point, that electric field into the charge Q is basically the external force. Now, why we are doing this integration suddenly? Okay, we are talking about work done, but suddenly we are doing integration because the force, this external force, is not constant. If it is constant, then our old formula, that is work done equals to F dot S, and there was a cos theta in case of there is an angle involved. In case angle is not involved, it is just F into S. That formula would have come, but in this case this force is constant. Okay, if this force is constant, you can use this formula. If the force is not constant, if the force is variable, then you have to use integration because this is not constant. Why so? Because F external, that is the electric field, is different at each and every point throughout this path. Now you might think that these 2 points are very close. Actually it can be close, it can be far, it does not matter. This formula is always valid. Even if the point B is far away, okay, you can still use this formula to calculate the work done. right? So work done, you have to remember that whenever the variable force is involved, to calculate work done, we have to use integration. This part you have studied in your first PU as well, but not so much application was there, right? Now this work done against the electrostatic force and gets stored as potential energy. So this is very important. See, this work done is actually stored as potential energy. At every point in electric field, a particle with charge small q possesses a certain electrostatic potential energy, right? So at any and every point along the in an external electric field, suppose we have an electric field, okay, and if you have some charge kept at some point, each and every point this q will have some potential energy, okay, it will have some potential energy. Now in practically we are not super interested in individual potential energy, but rather we are more interested change in potential energy when you move it from say point A to point B. Okay, we are interested in the change in potential energy rather than actual potential energy or absolute potential energy. Absolute potential energy we will not be super interested on. So let's see that the work done by external force increases its potential energy by an amount equal to potential energy difference. That's what I was talking about. Okay, so the amount of energy it gains, it can be positive, it can be negative, as I said previously, but for simplicity I will say, let's say it is positive. Okay, negative numbers, some students often get confused with negative energy, so don't go into that path. We are all positive energy, we will all have positive energy because we are trying to crack KCET 2026 exam. So we will always imagine that we have potential energy, and that is always positive. So the day by day you are studying, more you study, more potential energy you will gain. Okay, and during the exam, when you are writing the exam, the potential energy that you have gained, you will apply that in the paper, and the potential energy will convert into your kinetic energy, that is your score, right? So let's see. So the work done by the external force increases its potential energy. So more work is done, more potential energy is stored, right? And this is basically potential energy difference between points A and B. So potential energy difference between points A and B. Thus the potential energy difference is given by and potential energy symbol. The symbol for potential energy is U. Okay, remember that it is not V. V is a different quantity, we will see that. So U is the potential energy and delta U represents change. Delta represents change. Right, so delta U is the change in potential energy, that is final potential energy minus initial potential energy. From A to B we are going, right? So final potential energy minus initial potential energy, that is equals to the work done. That is equals to the work done. The work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points, and it is independent of the path taken to go from one point to other. This is the fundamental characteristics of a conservative force. Okay, now in the comment below write down any other conservative force you might know. Right, you can please write it down in the comment below if you know any other conservative force other than electrostatic force. So what is the meaning of that? Suppose you are traveling from A to B, okay, and it does not matter which path you take. Okay, you take some random path or you take the straight path. Work done in all such paths will be same. Work done in all such path will be same. It is independent of the path taken. Okay, so that is an example of conservative field. Okay, conservative field, conservative force. Okay, whenever there is a conservative force, there is a conservative field as well. Okay, that's why electric field is considered to be a conservative field. Very important point, electric field is a conservative field. You have to remember that, because maybe in the exam there might be some, especially in your board exam, there might be some objective question where they will ask which of the following is not a conservative force or not a conservative field. So you have to identify it. Okay. The actual value of potential energy is not physically significant. The actual value, that's what I am saying. The actual value means, suppose I am saying UB or UA. These are the actual absolute value of potential energy at point B. This is the absolute value at point A. So we are not super interested in the absolute value or actual value, but we are more interested in the change. So delta U is the quantity on which we are more interested rather than actual values. Actual values we are not interested. Actual value of potential energy is not physically significant. It is only the difference of potential energy that is significant. Only the difference in potential energy, that is delta U, is very important. UB and UA is not so important. Okay, only the change is important. Now let's see one question. A particle of mass m and charge q is placed at rest in uniform electric field E and then released. The kinetic energy attained by the particle after moving a distance y is. This is slightly older KCET question, but even this is also a very relevant question. So let's see what is the question talks about. Okay, so first we have a uniform electric field. Uniform electric field means no matter where you put the charge, okay, the force acting on this, the force external which is acting on this will be constant. If it is an uniform field, if the field is uniform or electric field is uniform, then we can say that the force which is acting on it is also constant. That is the meaning of this term, uniform electric field. Right? Now, electric field is constant. So, what is the force acting on it? What is the external force? External force is basically Q into E. Okay, charge is given as Q. So, external force is Q into E. So, what is the work done? What is the work done to move this charge? To move this charge by a distance y. What is the work done to move this charge by a distance y? Is basically what I said. If the force is constant, then how to calculate the work done? Force times displacement. Force times displacement, that is QEY. This is the work done. Now in this question they don't ask you what is the work done, they ask you what is the kinetic energy. What is the kinetic energy? Now how to do that? There was a thing, there was a theorem that you studied in your PU1 which is called work energy theorem. Okay, in the work energy theorem it says that change in kinetic energy is equals to the work done on the system. Change in the kinetic energy equals to the work done on the system. Now change in kinetic energy here is given by basically QEY. So this is the change in kinetic energy, and change in kinetic energy basically represents, because it starts from the rest, that is equals to the final kinetic energy. So this is the answer, QEY. So as you can see, this is a very easy question, Only thing you have to remember is that work energy principle and how to calculate the work done. These two things if you remember, you don't need to go for any fancy answers, you just solve it and you can answer it quickly. Now let's move on to the next part. Now we are going to discuss about electric potential. Okay, electric potential is slightly different than electrostatic potential energy or electric potential energy. Now, because in the most cases we are discussing about static charges. Charges are not moving, right? A charge is kept at a point, or even if it is moving by application of some force. You are applying some force and you are moving it from point A to point B. It is not continuously moving. That's why the first two chapters are also called electrostatics. Okay, electric charges and fields and electric potential and capacitance, these two chapters are called electrostatics, because in this case we are discussing about the properties of charges when it is static. Okay, it is not moving. Moving charges will have a different meaning that we will study in the I think fourth chapter. Okay, third chapter also, but third chapter is very specific. More detailed study of moving charges we will study in fourth chapter. Now, electrostatic potential is basically given by potential energy per unit test charge. So what is the meaning of that? Potential energy per unit test charge. So in the first case, if you remember, where we had this plus Q charge, we had this plus capital Q charge and we are moving it from A to B. This was our plus Q, and we had a point A, we had a point B, and we are moving some small q charge. That was our first case, right? We are moving this charge from A to B. Now if you take this charge, this was our test charge. If you take this charge and make it 1, if you take this charge and make it 1, then whatever work is being done or whatever change in the potential energy, that is called electric potential. So electric potential is very specific. Potential energy is for any charge. Potential energy is for any charge, whereas electric potential is for one charge only. So if you consider potential energy to Coulomb force, Coulomb force is between any two charges, right? But electric field is very specific. When you have only one charge, one unit positive charge, whatever force it is experiencing, that is called electric field, right? So electric potential energy, you can compare it with Coulomb force, whereas electric potential you can compare it to the electric field. In fact, electric field and electric potential, they are related. We will see that after a while. But first of all, let us understand what is the meaning of that. So this is the symbol for electric potential is V. The symbol for electric potential is V. This is same V as you have studied in your Ohm's law chapter in class 10th. Or in fact you have studied Ohm's law in before that class 10th class as well. So whenever you have studied Ohm's law first time, the same V is this electric potential. Okay, so V here change in potential, so that's why delta V. And in most cases, if I say V and delta V are actually same. In physics, V and delta V are actually same. As I said, in individual potential at a particular point, we are not super interested. We generally are interested in change in potential, especially in the electricity chapter. V is equal to IR, that V actually delta V, that is not absolute voltage, that is a change, difference in voltage. In electrostatics, still we may use V at some cases, but otherwise delta V is more important. Okay, so change in potential energy per unit charge. So you have to divide that change in potential energy by Q. To make that charge as 1, what you have to do? Suppose I want to make 5 equals to 1. How can we do that? To do that, we have to divide it by the same number. To make it 1, we have to divide it by the same number, right? So if we want to make Q equals to 1, how can we do that? To make Q equals to 1, we have to divide the entire value by that Q. Okay, then Q will become 1. there are some expression of q involved in this case, q cancels, so that q becomes 1. Okay, so I think it was A and B, not P and R. Just to avoid confusion, maybe in this next slide we will use some different formula, different symbol, but for now we are using A and B, so let's use A and B only. So delta U was UA minus UB. Okay, and VB, delta V is basically given by VB minus VE, VA minus VB. Okay, I think there was one more mistake. It is final minus initial, right? Yes, small mistake. I hope it's clear now. Okay, so UB minus UA by Q, and here what is the meaning of VB and VA? VB is basically UB by Q, and VA is basically UA by Q. So if you divide this individually with Q, you will get the something called potential at that point. Now potential in electrostatic has a definition. In fact, you may need to calculate the potential in some cases as well. So if you take the first point or your starting point at infinity, if you start at infinity, okay, if you start at infinity means the distance that you can imagine, infinity is bigger than that number. Whatever largest number you can imagine or you can write, infinity is bigger than that number. Okay, it's a huge number. Now in physics it is relative thing. For example, if you consider distance between me and distance between your mobile phone or laptop and your eyes. Okay, if you consider that distance, compared to that distance between you and sun can be considered to be infinity, because sun is very far away compared to the distance between you and the mobile phone, right? So because that is maybe 10 centimeter, 15 centimeter, 20 centimeter, but distance between sun and earth is lakhs of kilometers, right? So that's why that distance can be considered to be infinite. It's a relative thing anyway. So if you take a charge, let's see the definition. Work done by an external force, very important, work done by an external force in bringing a unit positive charge. So as I said, if you take this charge infinity 1, and if you take that charge at infinity, okay, and bring it from infinity to a point in the electrostatic potential V at that point. So suppose, now this diagram is slightly misleading. Let me change that. Suppose we have, this is our point P, and we have a charge which is located somewhere at infinity. Okay, if you take that charge from infinity, and that charge is unit positive charge, okay, your best friend. I always say unit positive charge is your best friend. If you take this unit positive charge and slowly bring it towards your point P, if you take that charge and bring it slowly towards the point P, then whatever work you will do to bring that charge from infinity to that point, that work done is basically electric potential, particularly at that point. Now electric potential at individual point has a definition. Unlike electric potential energy, electric potential has a definition of particular point. Okay, when you will calculate it. Okay, so now let's see some notes. Potential energy and potential are not same. I already told you. Okay, work done to bring a unit positive test charge from point A to point B is the potential difference between the 2 points, delta V. If the work done by the external force is positive, then the potential difference is positive. Okay, if the work that you are doing is positive, then the work done is positive, then potential energy, potential difference is also positive. As I said, positive work, positive energy. If the work done by the external force is negative, then the potential difference is negative. For example, you are watching my lecture, suddenly you swiped and you go to some influencer's video where he is talking about how to build a body or how can you do something useless. So that is basically negative energy, negative work done, that you are not gaining anything, not any sufficient knowledge, right? Now let's see. Here we will derive the potential due to a point charge. This is the expression for potential due to a point charge, but we have to derive it. How to do that? For some time, let me hide this. Term. I will show it later on. Okay. Now let's see. So here we have the same system. Okay. Same system. Here we have a point charge, capital Q. Okay. And we are bringing a small charge, we are bringing a small test charge, small q, from infinity to our point of observation P. Okay, small q from infinity, this is our infinity. Okay, q started its journey here, at infinity, very far away, and we have to reach our destination, that is point P. This is your KCET target rank, which is less than 1000, right? So this is your target and you are planning to reach here slowly. So you started at infinity when you are very small, when you are a kid, you started your journey. Okay, so that journey is still continuing. Now you are somewhere between first PU and you have moved to second PU. Suppose this is the junction where you are writing your first PU exam to come towards your second PU exam. Okay, now why I am giving you this example, this is very relevant example. Okay, you started at infinity, you had no idea about KCET exam when you were a kid, but slowly you are studying so that you can crack KCET, you can crack perhaps JEE exam or any other exam. So this is like a railway track journey where the train started at infinity and it is somewhere between two stations. Okay, now why we are considering somewhere in between points? Because infinity is very difficult for us to tackle. We cannot handle infinity. Infinity is very far away, it is a very large number. So infinity is very difficult to understand. That's why we have considered a in-between point. So suppose this distance is R. Okay, this is our destination, and this distance say X. So this distance say X. The point A is located at a distance X from this charge Q. Okay, and the distance between A and B, which are very close, that distance is dx, very small distance. Okay, now what we are going to do, first we have to find what is the work done to move this charge from A to B. What is the work done to move this charge from A to B? For that, first of all, we have to understand what is the force that is acting on this charge due to this capital Q. What is the electric force? The electric force, say Fe. Fe is the electric force, or let me write FEL. C. This is the F electric force. So what is the F electric force which is acting on this small q charge? The electric force which is acting on this, from Coulomb's law, it is K capital Q small q divided by x square. Simple Coulomb's law. This is capital Q, this is small q. Okay, the distance is x, so this is the electric force which is acting on this charge. Now, what is the work done to move this charge from A to B? That is also very, very important. To move this charge from A to B, you have to apply an external force. You have to apply an external force, and this external force has to be equal but opposite to that of the applied acting electric field. Okay, so that's why I write F. both of them are E, so that's why you don't get confused. So this external force has to be equal and opposite. Why opposite? Because the external force, the electric force, suppose both of them are positive, the electric force will try to keep it away, try to push it away, right? But you want to keep it from infinity to that point, you are bringing it and it is stuck at some point, right? So if you want to bring it from A to B, okay, at that point you have to apply an external force. That external force is exactly opposite to that of the electric force. That is very, very important, right? Now what is the work done? What is the work done to move this charge from A to B? The work done is given by, and because it's a small distance dx, I say this work done is denoted by symbol dw. The work done is given by, okay, external force times the displacement. Okay, now you said, sir, you said that it is only applicable for constant forces, not for variable forces. Obviously here the force is varying. So I will say that this dx distance is so small, that we can consider that during this small distance the force is almost constant. Okay, this is a little bit deeper concept, so if you just asking me, that's why I am answering it. Okay, so this, between these 2 points, the electric force is almost constant, the external force has to be also constant. Okay, that's why I have written it like this. This is the, basically we are trying to construct an integration. So those who are not aware of integration yet, if it is not done in your class, I have done basic integration class in my basics in the bridge course class. You can go and check that out. Okay, basics of integration is taught in that class, so that you can understand what is the meaning of it. Okay, so dw equals to force external into dx. Now what is force external? Force external is basically negative of electric force into dx. What is the electric force? Let me save some space. Okay, I will need some space to complete the derivation. So what is the, so this is basically negative of electric force into dx. Now what is the electric force? Electric force we have already calculated, so it will be k q by x square dx, and there is a negative sign. So this is the work done, small work done to bring it from A to B, small distance. Now if you want to find the total work done, to bring it from infinity to point P, the total work done to bring it from infinity to point P, what you have to do? You have to do something called a definite integration. And the limits of the integration will be infinity to P. Again, I have covered it in my bridge course class. If you have missed it, please go and check that out. Okay, we will do the integration from infinity to P, and we will put this as our value. So dw from infinity till point P. Okay, this negative sign will come out, infinity. Now at point P, the distance is known, r, so I will say from infinity till the point r, because point P is a fixed point, the distance is known, that's why we are putting, these are called limits of integration. This negative sign is written over here. Now we will write whatever is left over here, k capital Q small q by x square dx. Okay, now those who have done differentiation, they know that if we differentiate a constant and a variable, then the constant comes out of the differentiation, right? If it is only constant, then it becomes 0. Similarly, for example, ax, if you differentiate it, okay, a comes out of the differentiation, right? Similarly, in case of integration as well, whatever is constant, that we are not bothered about, they can come out of the integration easily. So negative k q they are constant, they come out of integration. So what we have left with, we are left with infinity to r dx by x square. Okay, now dx by x square, we can write this as x to the power of minus 2 dx, right? This was 1 by x square, so 1 by x square can be written as minus x to the power minus 2. So this minus k small q capital Q integration infinity to r. Okay, sorry, now we have to do the integration. What is the integration? If you remember my bridge course class, if you have seen that, I have discussed. So I have discussed in my bridge course class, integration x to the power of n dx, okay, is basically x to the power of n plus 1 divided by n plus 1. Exactly opposite to that of the differentiation you have done. In case of differentiation, the constant comes out as a multiplier and the power decreases by 1, right? In case of integration, power increases by 1 and it is coming, the constant comes out as a division and it is also added by 1. Okay, so let's see what is the value. Minus k q x to the power of minus 2 plus 1 divided by minus 2 plus 1. Okay, so it becomes minus, and minus 2 plus 1 also gives you k q x to the power of minus 1 by minus 1. Now there was a limit also, if you forgot, there was a limit also, infinity to r. Infinity to r. Now because this minus 1 is a constant, you can take out that constant and keep it outside. Okay, you can take out that constant and keep it outside. So you will get this as, so the work done infinity to p is basically given by k q in 1 by x to the from infinity to r. Okay, so this minus 1 comes out and this minus becomes plus. Okay, and now we have written x to the power of minus 1 as 1 by x. Clear? Now we will put these values. These are the limits. So how to put these limits? First we will put the upper limit in place of x. That's it. If there was x square, then we will put r in place of x, so it will become r square, right? Whatever is value, suppose x square plus 2x plus 5x, x to the power of minus 1. So we will just replace the value of x with the upper limit. Okay, the powers and the multipliers will remain as it is. Okay, so here we will just replace it, we will get 1 by r minus next is whatever is the lower limit, now we will replace it with the x. Okay, in physics generally mostly we will deal with some easier integration, at least in this class, class 12th standard. Okay, different difficult integrations are not there in your curriculum, so only easy integrations will be covered in this class. Okay, so now, but for new beginners, it might still feel, you might feel it is difficult, but trust me, these are the one of the easier integrations. When you have completed integration in your mathematics, you will say, oh sir, that was very easy, right? Now 1 by infinity. What is 1 by infinity? If you remember that simple fact, 1 by 0 gives you infinity. Similarly, 1 by infinity gives you 0. Okay, 1 by, in fact, any finite number divided by infinity will always give you 0. So this becomes 0, so we get that k q by r. Okay, the other term is 0. So this is the work done to bring unit positive charge from infinity to the point P. So this is the work done we have calculated. But what is the definition of electric potential? Electric potential is basically defined by the work done divided by the charge. The work done divided by the charge, and if you put the value of Coulomb constant K, then this value turns out to be as simple as, there is one more correction, this is not small q, this is capital Q. Okay, this is our source charge. So the electric potential at the point P, Vp, is given by 1 by 4 pi epsilon naught Q by R. Okay, in simple words we can say Vp is K Q by R. Okay, where K is the Coulomb's constant. Okay, from this we can see that if you divide it by Q, okay, so this Q cancels and you get K Q by R. K Q by R. If you put the value of K, this is the formal value of electric potential. This is the derivation, and based on this derivation you will see a question might come in your PU final exam. This derivation is very important, not only because it comes in the exam, this is also very important because it's conceptually very important. You have done a lot of different things that you have not done in your previous classes. For example, integration, how to construct an integration and how to integrate it actually to find the value. Okay, let's move on. So let's see a comparison between electric field and magnetic field. Okay, so if you remember that electric field, not magnetic field, electric field and electric potential. So if you remember, electric field was given by KQ by R square, whereas electric potential is given by KQ by R. So here we have to the power 2, here we have only to the power 1, both inversely proportional. Okay, so if you are given two graphs and if they ask you which one is electric field, which one is electric potential, how to identify it? Remember that electric potential, because it is proportional to 1 by R square, when the value of R is very small, when the R value is very small, electric field is high. Okay, but when the electric value of R is high, electric field is very small. So initially electric field is greater than electric potential, but later on electric potential starts to dominate. Electric potential value is more compared to electric field. So here as you can see, this graph starts at a higher value. This graph starts at a higher value, that's why it is more away from the axis. The value is very high, it started at very steep value and it falls, and when it is falling very quickly and goes to 0. Okay, this is basically 1 upon R square graph. Whereas this graph, it is also almost similar, but it is starting off slowly. Okay, it is starting off slowly and then it is also decreasing, but it's decreasing at a slower rate. So this line, the red line, is basically the electric potential, and the blue line is the electric field. Okay, so the blue line is the electric field which starts at a higher value but falls down to 0 very quickly, and this is the R axis. So as you are increasing the distance from the source charge, okay, the value is very high but slowly it goes to 0, whereas for electric potential its initial value is low compared to electric field, but it is going to 0 much slower compared to electric field. Okay, so that is the so if you are inversely proportional to 1 by R square, initially you will have a lot of energy. I will do it, I will crack KCET 2026, but very quickly you will lose your energy and you will go flat. Arey no, it is not my thing. I will do some graduation or something. I will sell some tea somewhere. But just joking. But if you are 1 by R, then maybe you are scoring low numbers now, but later on you will be ahead of those who have very enthusiastic right now but slowly losing out the steam. Now here are the few students who didn't lose the steam and they continue to focus on their study, continue to gain potential energy, and that has happened because of their own work done as well as the external work done on them by our excellent Diksha teachers. So Diksha has offline campuses across India, not only in Bangalore, across India. Okay, Diksha Vedantu. And these are the few students who are the toppers of KCET 2026. They are from most of them are from Bangalore only, but we have campuses in Mysore and some other rest of Karnataka regions as well. So if you want to study from one of our offline campuses, please fill up the Google form given in the link below, or you can click on the link given in the link below. Click on that link, go to our website, and you can fill up the link, and our customer representatives will contact you for any further details. Now let's coming back to our chapter, electric potential due to an electric dipole. Now electric dipole we have studied a lot, right? So for example, we have found out the axial electric field due to electric dipole, right? There is a slight mistake. It will be not square, but what? It will be cube. Okay, so electric field due to a dipole on the axis of the dipole is given by P by R cube, 1 by 4 pi epsilon naught P by R cube. This is the electric field. Now this is not about electric field, this is about electric potential. Now electric potential, how can we calculate? Now this is basically about electric field at axis only. Okay, if you remember, we have done along the axis and as well as along the equatorial plane. Okay, so this is basically the electric potential. The derivation is not part of the syllabus. Electric potential is given by 1 by 4 pi epsilon naught P cos theta by R square. So wherever you go, electric potential is always 1 less than electric field. So for example, for point charge it was 1 by R square, for field 1 by R for potential. For electric dipole it was 1 by R cube, for field 1 by R square for electric potential. This derivation used to come in 5-6 years back, but of late I have not seen this derivation coming, so I can safely assume even the derivation, mathematical derivations is not there in the book itself. There are some process mentioned in the book, but that process is not correct. If required, I will cover that later on before your exam, not in this lecture. Okay, this derivation is not super important. This formula is very important. Okay, but the derivation for this is not super important. You can skip that for now. If it requires, if you feel that my teachers taught that in the class, I want a detailed derivation, I will do that later on before your maybe your midterm exam. Okay, now let's see what is the meaning of this. So meaning of this means at any point. This is not only axial, it is at any point. For axial point, theta is along the axis. Theta is along the axis, so theta is 0. Right? For equatorial plane, theta is like this. Right? Theta is like this. So in that case, theta value is 90 degrees. So you can see that for equatorial plane, potential is basically 0. cos theta 90. So equatorial plane electric potential is 0, but electric field is not 0. Also electric field is vector, electric potential is a scalar. That much I think is obvious. If not, electric potential and potential energy is a scalar quantity. Why? Because work done is a scalar quantity. That's why electric potential is a scalar quantity, electric field is not. Electric field is a vector quantity. Now potential due to a system of charges. Now let us discuss electric potential due to a system of charges. We did the same thing for electric charges as well. Suppose we have few charges Q1, Q2, Q3, Q4, Q5, Q6, and they are oriented at different distances R1, R2, R3, R4, R5, R6. Okay, what is the electric potential at a point say P? This is the potential, not potential energy. What is the electric potential at point P? So electric potential at point P is basically electric potential due to all the charges. You need to add them up. Okay, so basically it is nothing but sum of I equals to 1 to n. There may be another set of charges. I am saying I 1 to n means in this case 1 to 6. N is 6 in this case. It can be 10, it can be 20, it can be 30. So that's why this is the general representation, okay, of all the Vi. What is the meaning of this? If you are new to this kind of symbol, this means that this represents summation. This symbol represents summation. That means addition. Summation means addition. Okay. Vi means first term is you have to put I equals to 1. So V1. Next is you have to put I equals to 2. V2. Next you have to put I equals to 3, V3. So on up to number n. If suppose if this n is equals to 6, if this n equals to 6, then we have to continue this process up to I equals to 6. After I equals to 6, you will not put I equals to 7. That is not there. Okay, so n is the upper limit, highest possible value. So once you reach that highest value, you have to stop. That is the meaning of it. So V1 plus V2 plus V3 plus V4 plus dot 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 Vn is represented by this symbol. Okay, and this can be written as I equals to 1 to n. Okay, K Qi by Ri. Right, now K is constant, so it will come out 1 by 4 pi epsilon naught sum of I equals to 1 to n Qi by Ri. Okay, Q1 by R1, Q2 by R2, Q3 by R3, like that. Okay, so this is the formula for electric potential due to a system of charges. Now let us look into an important concept which is called equipotential surface. Okay, what is equipotential surface? An equipotential surface is a surface with a constant value of potential at all points on the surface. It's not a line, it is a surface. Surface means it's a two-dimensional thing or three-dimensional thing. For example, spherical surface is three-dimensional. If you consider a square surface, it can be a two-dimensional thing as well, but not a line. Okay, in most cases we will show lines because it is easier for us to show, but you have to imagine it's either a spherical surface or it's a square kind of surface. Okay, so we know that electric potential is given by V equals to 1 by 4 pi epsilon naught Q by R. Right, now if this charge is fixed, okay, if you take different values of R, you will get different values of potential. But what if you take same R but different locations? Okay, if you take same R but different locations, then you will get all the points have the same potential. Let's see one example. Here we have a point charge. Here we have a point charge. Now how can you take R but at different locations? For example, for Q, suppose we take this as R, this is also R, this is also R. All the points on this surface are at a distance R. Okay, spherical surface. Okay, all the points on this surface, in fact it is a 3D surface, so it goes out of the screen also, into the screen also. Okay, so all the points on that surface are having same distance R, right? So because the distance is same, okay, the potential on the surface is basically same. Potential on the surface is basically same. So for a point charge, equipotential surfaces are concentric spheres. For equipotential surface, for point charge, equipotential surface are concentric spheres. Concentric spheres means you can construct infinite number of spherical surfaces having this charge as its center, this charge at its center. So these are called concentric spheres. Center is same, called concentric sphere. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. Okay. So for example, electric potential, at this case electric field is in this direction, okay, and equipotential surface through the point, equipotential surface is, you can consider this tangential surface. This tangential surface and the electric field is basically perpendicular. In this point also, electric field is in this direction, surface is like this. So surface and electric field are basically perpendicular to each other. Very important point. Based on that, you might see objective questions coming in your board exam. Now this is a parallel electric field. Electric field is parallel in this case. Now you can see that in this case the equipotential surfaces are parallel planes. This is the two-dimensional planes. Okay, parallel planes. They are also having same potential. So this is a equipotential surface. So this has a constant potential V1. This one will have a constant potential V2. This one will have a constant potential V3. Okay. So now you also have to remember that as you are moving in the direction of electric field, even though the potential on this surface is constant, this surface is also constant, this surface is also constant, okay, the individual potentials are not same. So here the relationship is V1 is greater than V2 greater than V3. This is very important concept. We will apply it later on. But as you are moving in the direction of electric field, the potential decreases. As you are moving in the direction of electric field, the potential decreases. Electric field decreases, potential also decreases. Okay. So this is a few examples for positive charge. This is a equipotential surface. This is negative charge. This is for this is a dipole basically. This is a dipole. When positive and negative charges are kept at a point close to each other, you see this kind of structure. This kind of structure is seen for both of them are positive. Then you will see this kind of structure. Now let's continue. What is the shape of equipotential surface for a line charge? If you are given a line charge, okay, you remember we did it. What will be the shape of the equipotential surface? Answer that in the comment below. Answer this question in the comment below. So this is a way to check if you are listening to me properly or not, whether you have understood the concept or not. So for that, answer this in the comment below. What is the work done to move a charge on an equipotential surface? This question I will answer. This is the important question. Okay, so you have a equipotential surface. Suppose this is an equipotential surface, potential V, and you want to move a charge from point A to point B. What is the work done in this case? This is easy. So work done is basically related to potential difference. Work done is related to potential difference. What is the potential difference in this case? The entire surface has same potential. Okay, so work done will be, now what is work done we will discuss in a while. Work done in this case will be 0 because potential difference is 0. Because the potential difference is 0, that is V minus V equals to 0. This is a equipotential surface. So on the surface of equipotential, on the equipotential surface, the potential remains constant. So both points A and B have the same potential. Same potential means potential difference is 0. If potential difference is 0, work done is also 0. Very, very important question. The work done is equals to 0. And based on that, we have seen objective questions in KCET, in board exams as well. Now let us do one small derivation. One small derivation is what? Here we have a equipotential surface kept at a potential V. Okay, here we have a equipotential surface kept at a potential V. The next equipotential surface on the same line is kept at a potential V minus delta V. Electric field is pointing from A to B. Okay, A to P. From A to P. Now, as I said, electric field is basically pointing from lower potential to higher potential. If you remember, last slide we said that, right? So if you see that electric potential is pointing from higher potential towards lower potential. So if you move in the direction of electric field, electric potential decreases, right? Similarly here also, electric field is pointing from higher potential to lower potential. Electric field is pointing from higher potential to lower potential. Okay. Now what we are trying to do, we are trying to find the relationship between electric field and electric potential. That is our target. So how can we do that? So first we have to understand, if you are transferring a charge, say Q from A to P, you are trying to transfer, or basically you are trying to take a point charge from point A to point P. Okay, then what you have to do? First of all, you have to do some work, right? What amount of work you have to do? The work you have to do is basically force times displacement. Now here we are assuming that the distance between these two equipotential is very small, delta L. The distance between these two equipotential is very small. So we say this is very small distance, so force is almost constant. So what is the force acting on this charge? External, internal force. Internal force or electric force is basically Q into E. This is the internal force, right? So how much force you have to apply? Q into E. Force equals to Q into E. You remember I did it in the last chapter, first chapter. This concept was there, right? So this is the electric force. So what will be the external force? External force will be nothing but minus Q into E. Same value but negative sign. Same value but negative sign. So here it is basically external force, because work done is always done by external force, right? So external force is minus QE. So from there work done is QE delta L, right? So this is the work done. Now what is the potential energy difference? Potential energy difference can be calculated using two different definitions. One is final potential minus initial potential, obviously. So final potential is V minus delta V minus V, that is minus delta V. Okay, and what is the definition in terms of work? So delta V is basically work done divided by Q, right? So from here we get this is as minus E delta L. So from here let me do one correction over here. Let me use this for now. let me use this as plus. Okay, let me use this as plus for simplicity. Okay, now this is E into delta L, E into delta L, Q. So if you put that value, this Q will cancel. So minus E delta L, and also delta V we have calculated is basically delta V. So delta V is equals to minus E delta L, or we can write E equals to minus delta V by delta L. Okay, so this is the relationship between electric potential and electric field, but this is not 100% correct because we are not using perfect delta V and delta L can have any value. So we will use this from now, dV by dl. If you take that dl close to 0, limit delta L tends to 0, that becomes differentiation. So this is the formula for electric field. Now, or more accurately, we will write this as Ex equals to minus dV by dx. Now I will not be able to explain the meaning of it, but you have to understand that this formula or this equation is valid for one direction only. For one direction only, it is not applicable for multi-directional values. So if the potential depends on x and y, you have to use a different, slightly different formula, not this one. So okay, let me interpret this meaning of this equation. So I just said no, E equals to minus delta V by delta L, or E is given by minus dV by dl. So I just said that electric field basically points from higher potential to lower potential. So because of that, there is a negative sign. If you already take this as negative, then there is a problem. You will get a positive value because you already assume that this is at higher potential. That's it. Okay. Because we have assumed this is at higher potential, but in the final value we are getting a negative sign. This negative sign indicates that this is not plus, this is actually negative. That is why I change it in between the derivation. Okay, so the electric field is in the direction which the potential decreases steepest means electric potential will decrease. Suppose you consider this diagram, electric potential will decrease in this direction as well, in this direction as well, and any other direction as well. All the direction electric field will decrease, but this is the direction where it decreases the most, the fastest. Okay, this is the direction where electric field decreases the fastest, steepest. So that is why this is the direction of the electric field. The magnitude is given by the charge in the magnitude of the potential per unit displacement normal to the equipotential surface at that point. Okay, so this is the magnitude which is given by the potential per unit displacement, potential change in potential per unit displacement. So if you make that delta L equals to 1, then whatever is the change in potential, that will be equals to electric field. So that means if you are trying to find E is basically delta V when delta L equals to 1. So delta L equals to 1 will give you the change in potential will be exactly equals to change in electric field. This concept is very, very, very important. The entire derivation including the formula is very, very, very important for your all the upcoming chapters, upcoming concepts. This will be used a lot, and based on that we see a lot of questions coming in KCET, in JEE, in NEET exam as well. Okay. Now potential energy in an external electric field. Okay, suppose we if you remember in electric field chapter, first we discussed Coulomb's law. From Coulomb's law we went to the electric field concept, and then from electric field concept we came back to electric force again. So if you remember the chronology, so force was given by K, Q1, Q2 by r square. Okay, then we came to electric field. Electric field was given by K, only one charge, divided by r square. From here we came back to electric force and said it is basically Q into E. Right, this was the flow of information in the first chapter. Similarly, in the second chapter also, first we discussed about electric potential U, or change in electric potential delta U. Then from there we defined electric potential from energy to potential. Now again it is time for us to go back to electric potential energy from electric potential. Okay, for a single charge. First let us discuss single charge. Only one charge is there. What is the potential energy? When a charge Q is placed in an external electric field, the potential energy of the charge is given by Q into V, similar to that of force. Okay, here V is the electric potential at that point. So whenever we start with something which is known, for example two isolated charges, but eventually we end up with the unknown value where charge is not known but electric field is known. Similarly, in this case, the source charge is not known but electric potential is known. If you know the electric potential, you can calculate what is the potential energy. Okay, now we have two charges. Initially we have only one charge, okay, in an external electric field. Okay, so we have only one charge. So the potential was V, so Q into V will be the potential energy. Okay, now two charges are there. When two charges are Q1 and Q2 are placed in an external electric field, the potential energy of the system is given by, it is very, very interesting. We have a electric field. One charge is kept at point P, another charge say kept at point Q, two different points. Okay, suppose at point P we kept Q1 and point Q we kept Q2. So at this point potential is Vp, at this point potential is Vq. This is something new that was not there in case of electric field. So in this case potential energy will be Q1 Vp plus Q2 Vq. This is clear, same as this one. But there will be an additional term. There will be an additional term which is given by 1 by 4 pi epsilon naught Q1 Q2 by R. R is the distance between these 2 points, which is very, very important. So this is simple, this is simple. This one is the potential energy of these two charges alone. So if there is, even if there is no external electric field present, this will be the electric potential energy of these two charges only. Okay, so there will be a case we will discuss where three charges are kept in a system. Okay, three separate charges are kept in a system. What is the potential energy of that system? Okay, so that is very, very important to understand. So here we have three charges. So this one is Q1, this one is Q2, this one is Q3. The distance between them is R12, between them is R23, and between them is R31. Okay, so this is a system, no external field is present. Okay, so what will be the potential energy of this system? So first we have to assume no charges are present. You bring only, the slate is clean, we bring only one charge Q1. No external field is present, so the work done in this case is 0. No electric field present, so Q into V is 0. So first, to bring one single charge, we don't have to do any work. So first work done is 0. Second, we will bring the second charge. Now because of this initial first charge, there will be some potential energy at this point, potential at this point, electric potential. So you have to do some work in this case. What is that work done? That is K Q1 Q2 by R. 1, 2. This much work you have to do to bring it here. Now when you are bringing the third charge, Now both the charges are already sitting there, they are already there. So both of them will say that you have to pay some tax to me, you have to pay some tax to me. So the third work done will have terms K Q1 Q2 Q1 Q3 by R31 plus K Q3 Q2 by R23. So if you add all the work done, you will get the total energy of the system. This is the total energy of the system. So Q1 Q2 by R12, Q1 Q3 by R13 and Q2 Q3 by R23. So this is the total work done of the system. R13, I have used R31. Let me correct that so that you don't face any difficulty. So this was first work done is 0, second work done is this one, and the third work done is basically addition of these two. And because it's scalar quantity, you just simply add all of them to find the total energy of the system. This is very common. In fact, 4 charges can also be calculated, 5 charges can also be calculated. The number of terms involved will be much longer in that case. I am not going to discuss, but the easiest way to remember it, take any 2 charges, multiply them and divide it by their distances. So Q1 Q2 by R12, Q1 Q3 by R13, Q2 Q3 by R23. If there is a 4th charge, then again you have to consider any 2 charges and add them. All of them will be possible. Any 2 pair of charges and their distance, you have to add it into the term. Okay, if you increase 1 more charge, 3 more terms will be added to that. The final expression for U is independent of the way the configuration is assembled. What is the meaning of that? So the meaning of that is it is independent. I said first I brought Q1, next I brought Q2, third I brought Q3, right? That was my process. That is how I assembled the system. But if you say, sir, I want to bring Q3 first and Q1 last, what will be the potential energy in that case? So potential energy, they are saying that no matter how you bring up the system, first you, instead of bringing Q1, if you have brought Q2, okay, what is the potential energy? That would also be the same value. If you brought Q3 first, Q1 next and Q2 last, then also in that case the energy will remain the same. Okay, this energy equation is independent of how the individual charges are assembled. Okay. The potential energy is given by the present state of configuration and not the way the state is achieved. Okay. Now potential energy of a dipole in an external field. This is also very, very important. Here we have a dipole kept in an external electric field and we want to find the potential energy of the system. Like we calculated the torque, we have to calculate the potential energy of the system. Now if you remember, the expression for torque was given by P cross E, okay, or PE sin theta, right? Now in case of work done, okay, what is the work done? Work done is basically when you rotate that dipole by a very small angle. If you rotate that dipole by a very small angle, okay, whatever work you have to do, that work is called the potential energy, right? Now if you are changing the angle from say a fixed angle theta naught to a final angle theta 1, then if you integrate this equation, you get the total work done, and total work done is basically the potential energy, right? And in this case, now if you remember the integration, sin theta d theta is basically minus cos theta. Okay, so in case of differentiation of sin theta gives you cos theta. Okay, in case of integration of sin theta gives you minus cos theta. Okay, and if you take the starting point at this angle 90 degrees. Okay, starting point as 90 degrees and final point as any another theta, because at 90 degrees theta naught cos theta is 0, that is the 1 point. So you will start it here and then we will take it to some other angle. Okay, in that case the potential energy is given by potential energy due to a dipole equals to the work done will be given by minus PE cos theta, minus PE cos theta. So when we are starting from 90 degrees to any other angle, obviously at theta equals to 90 degrees potential energy is 0, but remember that 0 is not the minimum potential energy. So there is a very common question that at what angle the potential energy is minimum, at what angle the potential energy is maximum. Based on this equation, these two objective questions are very common, and most of the time I see that student answer theta equals to 90 because they remember cos theta and they remember cos 90 is 0, so it must be cos 90. Actually it is not, because it is a negative quantity. So for the negative quantity 0 is not the minimum value. The minimum value will be when theta is 0 degree. So when the dipole is aligned along the direction of electric field, theta is 0, so electric potential energy is minimum. Electric potential energy is minimum for theta equals to 0, and U is maximum. Can you tell me the value for theta equals to 180 degrees or 2 pi? Why? Because cos 180 degree is minus 1, so minus minus is plus, so plus PE is the maximum possible value. Okay, so when the dipole is invertly oriented, okay, invertly oriented, this is the this position has the highest potential energy. Okay, now the position when it is aligned along the direction of electric field, it is called the stable equilibrium point. Stable equilibrium point means even if you displace it slightly, it will keep on along the direction of electric field. And the point which is opposite to that of electric field, it is called the unstable equilibrium point. Even though it is in equilibrium, but if you displace it, it will go back directly towards its stable equilibrium point. So this is called unstable, this is called unstable, this is called stable. Okay, every object in the world tries to achieve the stable equilibrium, including you. Now let's see one question. The electric field and potential of an electric dipole along its axis vary with distance small r respectively as. Okay, so electric field and electric potential due to a dipole. So electric field varies as 1 by r cube and electric potential varies as 1 by r square. So this is the correct answer. Don't fall for this trap. Okay, this is for a point charge. For point charge this is correct. This statement is correct for point charge. This is for a dipole. These two are completely wrong. Okay, now let's see the homework questions. Pause the video if you want. Answer the question and mention the answer in the comment below. I will reply to you if your answer is correct or incorrect. Don't worry and don't take anything on you. It is better, it is for your own practice. I am not giving too many homeworks. I am only giving you 2 homeworks, and that also I am receiving answers for only 1 or 2 students who are regularly answering. Okay, and if you want to download this PDF, you have to join our WhatsApp channel. This is the homework number 2, by the way. So please check this question, try to answer it, and let me know the answer in the comment below. Also, one more thing, that what I was saying, that if you want to download the PDF, please join our WhatsApp channel. The link of that is given in the description, okay, where you will get all the updates as well as the lecture PDF of this video, right? With this note, I'd like to conclude this video, and if you have any doubts, any questions, please don't forget to ask me in the comments. I will try to answer as much as possible. I'll be back with the part 2 of this lecture. Till then, bye.